yeah, I can kind of discuss some topics and problems today, but then on Thursday we'll do the same. And that's just a lot more topics for you folks to cover. Just tell me if you had a chance to work on problems at all. We had, like, the topic before the last one was kinematics, and then the last topic for today's class was Newton's laws. So how many problems were you able to work on? Yeah, just to be clear, folks, it's not that I ask you to find whatever random problems. You all have the book, right? The 300-page book, F equals ma, and problems are like it's pretty straightforward to find problems from specific topics. You just look at the end of each year, and it lists problems and corresponding topics, and also the difficulty based on a 3-star system. So just pick out problems from there, and whatever problems you get stuck with or have questions, that's what we'll discuss. Yeah, that's fine. Well, let's see if I can get it. Is there any way for me to see it? No, it actually was getting better if you move it close enough. Okay, okay, yeah, if you can hold it still. Yeah, actually, move it a little bit closer, and I'll just do a screenshot. Okay, let me see if I. Okay, I'm not sure if I can read everything. So I see a bunch of things are given, but what's the question? What is it asking? No, what's the question? To find the acceleration? Uh-huh. Yeah, okay, this is very much in the spirit of what we discussed last time. Let me wait. How do I share? Just give me a second. I'm trying to find where the share screen option went. Uh, yeah, I'm not seeing the share screen option anymore. Oh, here, okay, here we go. Okay, do you see this picture? Okay. And just to simplify life, can just one person speak at a time, like can somebody who's close to the microphone, because it's really hard to. Yeah. So okay, yeah, this problem is pretty similar to the ones we discussed on like the Thursday before your break. Uh, you basically uh, you just need to find the acceleration. So you can use the black box trick we discussed and write the acceleration as F net external over M total. Okay. So, M total, just the total mass. Now F net external is the total. Um, oh, I apologize. Yeah, M total is the total mass. Now F net external is the the total external force. If it's not like immediately obvious, you just start by doing free body diagram for each object involved, and you can think of the two blocks and the string, but the string is massless, so it doesn't contribute here, and friction is the same throughout the string. But at the end of the day, you're going to realize that this is the first external force, and yeah, I don't see, is there a friction? Oh, okay, there is something about friction. So there is friction up the hill or maybe down the hill. We'll figure it out, right? And then there is also the horizontal component of gravity. So let's call it MA G parallel. Okay. Yeah. Is everybody okay so far? Okay, so now what determines the direction of friction? You need to compare these two forces, right? They compete. So whichever force wins, friction will be opposite to the winner. Okay? That's when you start, that's when you need to start looking at the numbers. There is no other way. But does that give you enough hint? Do you think you can finish it off, or you would like me to bring it to completeness? Are you guys saying you can't see the picture? Okay, well, let's put some information here. Just tell me what's given. I see the angle is 30 degrees, right? If I can read it, okay. MA is 10 kilograms. The coefficient is 0.2, right? And then is this 8? Uh-huh. Okay, and that's pretty much all we need to know. So yeah, we need to find A of B. Yeah, so what is G parallel? G parallel is G sine theta. Make sense? Yeah, I don't remember if I explained it some time ago or not, but if you forget, there is really two options, and you need to choose between the two, sine theta, cosine theta. The quickest way to figure out which of the two functions to use is to use the trig trick. Let me just, did we talk about it at all? Yes? Yeah. So basically you set theta to 0 and see what happens. Because from common sense, if the angle is 0, the component of gravity parallel to the slope is 0. So we expect G parallel to go to 0. Okay? So this expression does, but if you picked cosine, it wouldn't have. So that's how you figure out very quickly. Does that make sense? Okay. So anyhow, you need to compare. You need to compare MA sine theta and MB. You familiar with this symbol? Basically means compare. What's that? What do you mean not drawing? Wait. How do you know it's blue if you don't see it? You see what? Huh. Um, uh, wait. So what? Can you share your screen? Yeah. Yes. I'm. You. So can you see black though? Oh, that's weird. Um, so, but you see the photo with the problem. I can make another screenshot and. Okay. How about now? Okay, yes. Probably I'm sorry. I probably chose some wrong screen or something. Yeah, so you should see everything now. Okay, let me remind you. This was the first thing I wrote. This is the starting point. The formula we got last time, the black box track. Okay, and M total is straightforward. F net external is what we need to find, and I started doing the diagram. I only drew the external forces. Well, not exactly. So basically, what this mg parallel represents, it represents the net force of normal and gravity. Does that make sense? Okay. So these three are the external forces. All the tensions are internal, so I'm not drawing them. They don't contribute in this numerator. Okay. Yeah, this is the symbol which I'll use for compare. I'm not sure if you're familiar with this, but this is what we'll typically use if we want to say compare. So we compare MA sine theta and MB. See who wins, okay? Since theta is 30 degrees, this is 1/2, and it looks like B wins, right? Okay, so that means what? That means we need to correct the diagram, right? That means friction is actually pointing this way. Make sense? Okay, then. So then things are pretty straightforward from here. So what you need to do is to write F net external equals G times MB minus MA sine theta minus friction, which is, yeah, what is friction here? It's mu n, which is mu m a g cos theta. You folks remember this combo for the normal force? Okay, so you got mu m a g. Okay. G is no longer in sight. No G. Okay. Yeah, let's just see if it makes sense. MA is 10, so we got, this is 5 kilograms. And this is 2 kilograms. Okay. So we got some positive number. Right? We got 1 kilogram effectively inside. So F external is 10 newtons divided by the total mass of 18 gives you the answer. Okay? Oh, yeah, right. Cos theta, thank you. So, yeah, please incorporate that. Yeah. So you subtract a little bit less. So you have a little bit more than 1 kilogram inside. So the force is a little bit more than 10. Yeah. Yeah, I cannot read. I'm not sure what this number is. Is it, what, 0.89 or something? Oh, you did? Where? Yeah, let me see. Yeah, okay. So, but it looks like we got everything that we needed to, didn't we? Yeah, the acceleration is down the plane, and 0.69 sounds like a reasonable number to me. What do you think, folks? Hello? Yes. Yeah, that's one of the first things we figured. It goes down. Yeah, if somebody asks a question, please, the person who is next to the microphone, is that Andrew? Yeah, just repeat the question if somebody asks a question. But are we good on this problem? Okay, perfect. Anybody has any other questions? Yeah, the resolution's there. So basically, you ask me only if something is still unclear. Uh, can you send me the problem? Well, it depends on what the question is. Is the question about something in the solution? If that's the case, just send me the solution and ask the question. Okay. Oh, okay. Okay. Yeah. That's. Yeah. Let me just check it out. Yeah. Okay. So you have a question about the first paragraph, right? The one that doesn't use calculus, or the second. Yeah. Can you clarify your question? Mm-hmm. Yeah. Okay. Yeah. I'm still trying to figure out what exactly they mean. So yeah, the analogy with harmonic oscillator is tempting to use because the force is said to be proportional to the depth. So it's like compressing a spring oscillator. Um, yeah, I'm not sure about the second part. The amount of contact. Um, yeah, I need to think about it. I'll get back to you on this. Okay. So I could wait. I want to get some rigorous uh, explanation to you. Yeah. So I'll get back to you on this. Okay. Hello. Okay. Um, yeah. Any other problems, or I don't know, it takes like at least 5 minutes to actually for me to get the problem, then another couple of minutes to think about it. I'm not sure if it's productive. So um, you can send me some stuff. I'll start explaining, not super new topic, but I just feel that we'll spend time more productively, and then I'll be looking at the problem on the side of the screen, and if I have some explanations, then I'll explain. So if somebody else has additional questions, then let Andrew send the pictures to me. Okay. Oh, okay. Let me basically build on top of the previous topic. Okay, I'm not sharing the screen right now, right? Okay, let me. Yeah, so we started talking about Newton's laws, and I gave you some problems. Nobody got back to me, so I assume you did fine, but let me know if that's not the case. Oh, okay. Let's continue. So last time we focused on inertial frames, but let's talk about non-inertial frames. Oh, you want the definition of this? Okay, let me give you simple but not very proper definition, but hopefully it makes sense. So what typically we mean by inertial reference frame is a frame that moves with a constant velocity with respect to a laboratory frame. So the bad thing about this definition is that it's not clear what laboratory frame is. You can think of it as a frame associated with the classroom for now, and as a stationary frame. But last time we discussed a better definition. A better definition would be it's a frame in which law of inertia holds. So everybody knows law of inertia, right? An object will keep moving at a constant velocity or remain at rest if not acted upon by forces, or forces are balanced. So this is the law of inertia, and it holds in inertial frames. So if you say sit on a train and the train either not moving at all or moving at a constant velocity, then and you put a steel ball on the table in the train, then steel ball will stay there. It won't roll. But when the train is taking off or braking, it won't happen, right? The ball will start rolling all of a sudden. And that's how you know the train at that moment is not an inertial frame. Does that make sense? Okay, perfect. So, and actually, I want to focus on the situation when you have a non-inertial frame. So non-inertial frame, again, roughly speaking, you don't have to test it with the ball every time. You just think of, does it have an acceleration with respect to the laboratory frame? And if it does, it's not inertial. Two quick examples. A train or a car that's accelerating. So if you have a car that goes with some acceleration, then a passenger in the car, what would he feel actually? Yeah, the person would think that something is pushing him in the opposite direction, right? Think of a car that's taking off, right? You feel that there is a force pushing you in the opposite direction. F. We'll call this force of inertia. Okay, so this is anti-parallel to the acceleration vector. So A is the acceleration of the frame. Of the frame with respect to the lab frame or the stationary frame, okay? Another example is an elevator. So if an elevator is accelerating up, like when you're in the first floor and just start going up, what do you feel? Yeah, you feel that as if something is pushing you down. Like in addition to gravity, you feel this extra force. Okay. And one last example, just to make things a little bit more interesting. If you have a rotating reference frame, let me do it separately. Deserve a separate place. If you have a rotating reference frame, let's say it's rotating counterclockwise. Then let's say at a constant velocity or angular velocity, and there is still acceleration to the frame, right? So centripetal acceleration. But then if you have, let's say, a ball somewhere here, there will be a force, and now you can guess, you can tell me which way the force will be acting. What's that? No, okay. Tell me which way this force will be directed. The force of inertia. Yes, outward. Okay, you must have seen it, right? If you think of, say, merry-go-round, and you place a ball, you realize the ball will want to roll off, right? Outward. And again, it's not that there is a force acting on it, it's because of the reference frame. There is no physical force from some other object that acts on the ball this way. It's a fake force of inertia. But the main feature of all forces of inertia is that they are antiparallel to the frame's acceleration. In fact, in this particular case, this is away from the center. It's called centrifugal, right? Centrifugal means away from the center. But again, keep in mind, centrifugal force is not a real force. It's a fake force of inertia. In fact, let me put this down. Force of inertia is a very simple thing to have. It's actually minus ma of the frame. Minus takes care of the direction, and the force of inertia is actually proportional to the mass of the object that you consider, like the mass of this person here or the mass of the ball in this example. Does that make sense? It looks very much like gravity. For example, in this example, if you take this elevator in the outer space, no planets, no stars, no gravity, but then accelerate the elevator up with A specifically chosen to be equal to G, force of inertia would be precisely equal to force of gravity as if this person was still on Earth. So there would be, let's say, if there are no windows in this elevator, there is no way for the person to tell the difference, whether he is still on Earth, stationary, or in outer space accelerated at G. And this simple example is actually called Einstein elevator. This was an example used by Einstein to demonstrate the so-called equivalence principle, one of the foundational principles of general theory of relativity. He said, you can imitate gravity by choosing an accelerated frame, or vice versa. You can choose a reference frame, accelerated reference frame, so as to kill gravity. So Einstein's elevator. Yeah. Andrew, can you repeat the question? Why this ball rolls out? Well, it's the same explanation as here. Law of inertia, in particular, object will stay at rest if not acted upon by forces. That law only holds in inertial frames and doesn't have to hold in frames that accelerate, and it doesn't. Is that a good enough explanation? Yeah, so if this example doesn't surprise you, then this shouldn't either. It's just a different structure of acceleration, right? But there is always this force of inertia opposite to acceleration. Yeah, acceleration is inward. Acceleration of the rotating disk is inward. The force of inertia is opposite to it, so it's outwards. Let me just throw this in and we'll come back to the rotating example. Okay. As you probably know, there is one more force associated with rotational motion. Do you know what force I'm talking about? What's that? There is a name. I'm just not hearing. Like, unless it's Andrew who's speaking, I can't really understand what you guys are saying. Well, torque is not a force. Okay, let's be clear, folks. So there are real forces that I hope we covered last time, but let me remind you. The way to tell if there is a real force is that force is something characterizing an interaction of at least two objects. Okay, so if you say there is a force, a real force, you must be able to present a pair of objects that interact with that force. So when you say there is force of gravity, what you're really saying is that there is an interaction between a person or object with Earth. Okay? If you say there is normal force, that what you're really saying is that there is a surface that's exerting this force on the object attached to the surface. But forces that you call centripetal or centrifugal, it's not their real name, right? You got to present an object or like two objects. Some of the real forces may act as centripetal. Say, if you whirl a stone on a string, the tension from the string on the stone will act as a centripetal force. But centripetal force per se just doesn't exist. There is always there has to be some real force. Okay? So this is all the past stuff. That's before we started considering non-inertial frames. Does that make sense? Okay. So if you say there is centripetal force, you must be able to say like which real force it is, or a combination of real forces that act as centripetal. But now, if we're dealing with non-inertial frames, you get this additional fake forces of inertia, but they're very simple. They just defined by this equation. And don't get me wrong, Newton did this. I'm not sure why it's not included in the standard Newtonian mechanics course, but Newton did all this. He basically introduced this for his second law to work in non-inertial frames. Like, if you still want to have F net equals ma, you got to include this additional fake force. That's how he originally introduced it. Okay, but back to my question. So when you have a rotating frame, there are two forces. There are two fake forces. One is just this centrifugal force that's defined as minus ma centripetal. But there is one more force. It has a name to it. Have you heard of this guy? Yeah. Okay, good. So let me explain. So let me first explain it on a disk. So it only starts acting if a ball is rolling radially, away or toward the center. So if there is a velocity to it, okay? If the ball is stationary, Coriolis' force is 0, okay? Let's say you got omega. Is everybody familiar with vector omega? How it's defined? So use right-hand rule. Basically, make your fingers curl with the omega, with the rotation, and stick your thumb out, and that shows you the vector omega direction. So in this particular case, vector omega is out of the page. Does that make sense? Yes, of course. And then the direction of omega is a convention, but it's a good one. It's a good one because I don't know. Let me stop sharing the screen for a second. I'll illustrate. Okay, what if I make a rotation like this? Which way is it rotating for you? Clockwise. For me, it's counterclockwise. So if we try to describe rotation in terms of clockwise versus counterclockwise, we will disagree, right? Neither of us is wrong. We're just using a bad way to describe the motion. But if we use our right hands, and I rotate my fingers the same way as before, I stick my thumb out, I say my vector omega is pointing toward me or into your screen. So if you use your right hands, you will agree with me on the vector omega. It is a convention. We could have defined it using left hand, no problem with that. But once we decided, we stick to it, and that makes everybody agree, no matter what perspective you're looking at. And that's what makes a good definition, okay? So that's why vector omega is a good thing to use. So let me share the screen again. So omega is out of page, okay? So Coriolis force is 2m omega, oh, let me not use the bracket, omega cross v. Let me see if I got it right. Actually, I got it wrong. It should be v cross omega. It's the other way around. And you'll see why, okay? So first off, if the ball rolls, imagine for a second that the disc is not spinning. Then the ball will just roll straight off, right? Suppose you kicked it from the center and it just rolls straight off. But if the disc is spinning, and let's say you painted the ball so it leaves a trace on the disc as it rolls, which way, what would the trajectory of the ball look like? So it would curve backwards, right? Does that make sense? Yeah, so what does it mean? That means there is a sideways force, sideways acceleration to do that. Okay, so Coriolis' force is perpendicular to both omega, which is obvious, right? That means it's simply in the plane of the picture, right? But it's also perpendicular to the velocities. Velocities is, and the actual direction, say in this particular case, perpendicular to velocity may mean either to the right or to the left. So you determine the actual direction by using the right-hand rule. So if you do v cross omega, you guys do that, right? And you will see that the force is actually to the right. Does that make sense? Okay. Or Coriolis force. Yeah, so it's easy to understand when you roll things on a disk. But now think of the Earth. So let me give you a quantitative example, because I suspect you may have heard some weird things about how Coriolis force is responsible for the direction of the whirl in your toilet. Have Has anybody heard that? Do you believe that? You can tell by the tone of my question. Yeah. Okay, so let me give you a quantitative example, and then you can evaluate the toilet example yourselves. So if you drop a penny from a 100-meter tall building, in fact, you have a lot of these buildings around you, right? So 100 meters. So if you drop a penny, assuming no air resistance, no wind, so presumably the penny would just drop straight down, would it? But because of the Earth rotation, what happens is that, let me kind of illustrate it, not up to scale, of course. So here is Earth, and here is the building, and the Earth is rotating. So what happens as the penny drops, it goes radial, right? It goes towards the center. So that means it will be deflected. It won't drop precisely where it would. It would deflect slightly, okay? Is it making sense so far? So, okay. So the amount of displacement, it's some problem to work out. It's pretty tedious thing, but just to give you a sense of scale, for 100-meter height, x would be about 3 centimeters. And it's proportional to the height. Let's say if you have a 200-meter tall building, x would be 6 centimeters. Okay. Now scale it down to your toilet. What's the height of your toilet? Yeah, okay. So scale it down 400 times. What do you get? You get a tiny fraction of a millimeter, right? So no way this force can be responsible for the direction of the whirl in the toilet. There are many more significant forces in the toilet that determine that. But people still say, oh, in the northern hemisphere, the toilet whirls one way. In the southern hemisphere, it whirls the other way. No, that's not the case. It does affect how the rivers flow, though. For rivers, the speeds and masses are much more significant. So Coriolis' force does affect how rivers curve on Earth. And also how, what do you call those? The air vortices, like how hurricanes form and such. So Coriolis' force does have an effect on those because speeds are much more significant and height scales are also much more significant. So for those phenomena, yes, Coriolis' force is significant, but not for the toilet. I have not seen problems on Coriolis' force on F equals ma, to be honest. But I feel that you kind of need to know it anyway. Do you folks have any questions about what we've gotten through so far? Okay, so let me give you another example. I don't think we talked about it. Not far from me, there is this closed facility with a huge centrifuge arm where they train the astronauts, or used to train astronauts. It shut down maybe 20 years ago, but that's where they also trained Neil Armstrong, the first person on the moon, because they could imitate weightlessness and things like that. But another interesting thing, what they train pilots for is this. So think of a carrier like a large ship with planes. So are you guys talking to me? Ah, okay. Okay, are you with me? Yes. Okay, so yeah, let me explain what this example is about. So carrier planes, they have a very short runway. That means in order to pick up a speed needed to take off, they have to accelerate much more dramatically than regular planes, right? So that creates some extra G's on the pilot, right? That's no surprise. But what's interesting is that think of a pilot inside this plane and significant G's. That's part of any pilot or astronaut training. But hello, are you with me? Okay, so but there is another very interesting effect here. So this is the regular G on a pilot, or you can say mg for now. Okay. Now, if the plane is accelerating to the left with acceleration a, there is force of inertia, right? Which is equal minus ma. So what the pilot perceives, and again, I kind of randomly drew it of the same length as g, but it may be longer, maybe shorter. It's comparable, okay? So the bottom line here is that let me first ask you a question, folks. What started happening when they just started, testing carrier planes, what would happen is that the plane would take off, and then shortly after, it would dive. Okay? And they found out it was because of the pilots. The pilots directed the plane into the water. So they tried to understand why they did this. Maybe you can explain, or if not, I can continue. Well, think about this. If the plane is going parallel to the water, it's not moving radially. So again, Coriolis force only arises when you have a radial velocity. No. What really happens is this. If you look at the net force on the pilot, what pilot thinks is that it's somehow mg effective, where g effective is directed along this diagonal. Does that make sense? So the pilot perceives this extra G is pushing him backward as an extra G, as if force of gravity became diagonal. Like you can kind of experience a similar thing on a passenger plane. If you yeah, I suppose you guys have flown on a passenger plane. When it's like speeding up to take off, you feel that you're being pushed back, but at the same time, if acceleration becomes very significant, you kind of start thinking that gravity is like, that down is not like straight down, but diagonally down. Does that make sense? So what does it mean for a pilot? If the pilot is like if the plane is taken off and going horizontal, if the plane is going horizontal, oh, probably not the best color. Yeah, if the plane is going horizontal, as it should, the pilot, what does the pilot think? Let's rotate the picture. The pilot thinks that down is this. That means the pilot thinks that velocity is actually going this way. Does that make sense? And what do you do as a pilot if you think you're climbing up? You try to straighten it, right? But that exactly causes the plane to dive. Make sense? So this is like V prime. Then in this picture, V prime is like this. So how do you fight this? You can only train people not to do this. You can like train the people to resist their sensations and, you know, understand it's normal. It's normal that your gravity doesn't seem to go the right way. Okay, so this is an interesting application of non-inertial frame. Now let me give you a more concrete problem that actually was on F equals ma exam, and that's actually a problem that I created. So think of this. It was in 2017. So you have two blocks on top of each other. And let's say for simplicity, mu is 0 between the bottom block and the surface. But there is a non-zero mu between the blocks. Okay? You apply a force to the top block, F. So I can give you the masses of the blocks. M1, M2, and mu. Here is what you need to find. So imagine this: if you apply a very little force, what do you think will happen? What's that? Yeah, they will move together, right? They would not move with respect to each other. They would just slide as a whole. Okay? Now, let's take the opposite extreme. If the force you apply is huge, what will happen? Yes, exactly. So there must be some value, some minimum value of the force such that the top block slides across the bottom one. And that's what I want you to find. Find the minimum force such that one slides with respect to 2. So I think it's a good time to take like a 4-minute break. What do you think? And you can think about this problem and then we'll come back to it. How about that? Okay, so yeah, take a few minutes, think about it.